Thanks for clicking over this video. If you wanted to know power budget and power distribution network analysis on Altium tool, then this is the correct video you have clicked on. Now let's talk about what are the topics we're going to cover in this video. In part 1, we have created the power budget for level 4 complexity. And as you can see on the screen, all the blocks are created on the left side of the screen. On the right side, I've created a netwise block diagram. If you wanted to know how I've created power budget and netwise block diagram, then click over I button, it will direct you to part 1. We'll start with a little bit discussion from netwise block diagram and how I've created it using schematic design. Then we'll put all the information from power budget and netwise block diagram to PDN tool of Altium Designer, and then we'll simulate it. After simulation, we'll analyze the results and try to implement in case of any fails happen on our original design. Then we'll try to make those simulation working for all the test cases. Who don't know which tool I'm using, it is Altium Designer 22.1, and if you wanted to get the free trial of that tool, I put link in the description. You have to just click there and register yourself. Within 24 hours you'll get the license. PDN Analyzer tool is a separate license from Altium Designer, so for that I have put a separate link. For purchasing PDN tool license, you have to click over that link. With that said, let's roll the intro. Netwise block diagram is nothing, just a designator and net naming representation of all the blocks we have created on power budget. So we will see for DC jack, I mentioned its designator, which is J8, and what is the net name that is connected to the positive pin of DC jack, and what is the net name on the negative pin, which is ground, and in positive pin it is VM. Now further the block, another block is our LDO, which is 7805. I have noted down the designator of that as well, which is U8, and it is further connected to 5 volt. Similarly for LD1117, the designator is U9 and it is connected to 3V3. And similarly you can see all the other blocks. Now on block 2, it is a further extension of plus 3V3 output of LD1117, and here these are the loads which are connected to this regulator. So I mentioned these with their designator naming and what are the nets that are connected if it is required. If there is no mention of any net, then we don't need to use it on our PDN tool. Similarly, I've created the net naming of block 3. As you can see, FB1, so there are, FB is nothing, just the ferrite bead connected in series, which is responsible for providing noiseless power to our load, which is U1, and U1 is connected to ground. So this is what we need to feed in PDN tool of Altium Designer. So let's put all this information from power budget and netwise block diagram to Altium tool. Go back to our Altium Designer. We'll go to PCB file and make sure before going for PDN Analyzer, your stack up information should be very accurate. Whatever the PCB you're going to manufacture, there should be mentioning of all the types of vias you have used, and apart from that there shouldn't be any design rule errors. Okay, whatever the DRCs, make sure all the DRCs should pass. Okay, now go to tool, click over PDN Analyzer. All right. So first step is, as you know from previous levels, we have to select all the nets and fill the right value of voltages on each of these, and that is why we have created our power budget. So we'll start with VM and its voltage should be 15.5. We'll search for VM here. It should be at the last, okay, and its voltage should be 15.5. Add selected. Let's go back to our power budget. Another voltage we want 5 volt, 3V3, and yeah, these are the voltages, 5 volt, 3V3 and ground. Let's select those as well. So we want 3V3, 5 volt, which is fine. Look for ground. And you can make this power budget in very detail if you want, but you can ignore in case of some microamps or very low milliamps loads are connected on these power pins. Ground, let's search for that. I can't able to find it. Okay, add selected, and its voltage should be 0. Let's look for another nets if required. So I don't think any other net requirement is there. These are all the nets which are responsible, and it's pretty much easy after creating the power budget. The complexity was more on power budget because it has separate 3 blocks which are further connected to 3V3 and 5 volt, and I just wanted to tell you how to analyze those. So I don't think we need anything else. Let's move further. After adding those, we'll click OK. Another step is we'll go to file and make it compact. Now let's save it. So we'll name it level 4 PDNA, and if you want you can rename your simulation. In our case I'm okay with that. Now here we need to fill all the information. So the first thing is we have to select the nets of ground, double click on this. So this is our VM net. Now here we have to add source, right click, add source. So what is your source? So there are 4 options, and in our case it is voltage source, and that is coming from J8, right? So that is why I have created a designator based block diagram, so which will be really useful when you are creating the PDN network. Now here we have to fill few parameters. So Vout is already filled, Iout max. So you should make sure whatever the source or whatever supply you are using, what is the maximum current of that. So in my case it is 5 amps. Okay. Now there are further loads which are connected. So on VM there are 3 loads. One is U8, U9 and Q2. So let's connect those as well. Right click, add load. What are the type of load which is connected? So first is voltage regulator. This is linear voltage regulator, which is our 7805. Its Vin is U8. So it's automatically selected all the pins. Here I have some doubt. Okay, so this out you have to make sure it is selected correctly. So in our case it is 5 volt. Now the pins are right. What are the parameters? So this V out will be 5 volt, not 15. R out, R bias. Okay, make sure you have selected the correct value of I out max and power dissipation max through those voltage regulator. Now click OK. So one load is added. Let's add another load. That will be our 3V3 regulator, and it is again a VRM, and its designator is U9. V out will be 3V3. Now here we'll select correct voltage, correct value of current, and correct power dissipation. Press OK. Now we'll add another load, which is our Q2 or motor driver, and further on motor driver we have connected a MOSFET, so which is solely responsible for all huge amount of current of this circuit, which is 3.5 amps. So we'll add another load, that is a IC, and on that the designator of that is Q2. Alright, and ground is connected through a sense register, which is R77. So let's add that. Alright, what is the load current on that? 3.5 amps. Minimum and maximum voltage, it is not you need to fill, but in case of any limitation you can add that. For example, your motor driver or whatever the motor you wanted to run, it is less than 15.5, then you should put it here, and from that it is obvious it can't able to handle if it is less than 15.5, it can't able to handle VM, right? Because in our case it is 15.5. So you have to make sure you're putting values here if there is any limitation. If not, you can just leave it 0 volt, which is our don't care. Press OK. So we have added another load. Now further on this network, these VRMs are further connected to different loads. So let's go for U8, which is our 5 volt regulator, and you have what you need to do. You have to just right click and left click over add VRM to network. Now here we need to add other loads. So on 5 volt we have U1, U3, and some resistive load are connected, and then we have U4. So let's connect these loads quickly. So we'll go for U1 first. So right click, add load. Our first load is a IC, so that is connected through FB1 or Farad bead 1, and its ground is connected through U1. What is the load current of that? I have mentioned here. So for U1 and U3, the load current is 1 microamp. Okay, so let's add that. 1 microamps is a really small current, but we'll do it. For micro, I use small u and capital A. Minimum and maximum voltage requirement is plus minus 5%. Press OK. Now we'll add another load, which is FB3 and U3. So that is again IC. Let's select FB3 and U3. Load current is same as 1 microamp, and for voltage we have limitation of plus minus 5%. Let's add another load, which is a resistive load, and on that we have 8 10k resistors connected parallelly. So the resistance will be so we have 8 10k resistors connected parallelly, so resistance will be 10k divided by 8, right? So if we will do that calculation, 10 divided by 8 will be 1.25k, or 1.25k is fine. All right, so just remember that the resistor of 8, I'm just noting down that. Okay, let's go back to Altium Designer, and that resistance is U4 and ground is through U1. So let's select U1. All right, now you have to enter resistors, so that we have measured it is 1.25k, and minimum voltage will be plus minus 5. Okay, now we'll add our another load, which is U4 coming from Farad bead. It's again a IC and U4. What is the load current on that? It's 0.1 microamp. It's really small, but still we'll consider it. Plus minus 5%. Okay, so these are all the loads connected on plus 5 volt. Now we'll go back to our first network and create or add load for 3v3 as well. So we'll right click, add to VRM. Now for 3v3 we have a couple of more loads which are connected. So let's do that quickly. So add our first load, that will be U6, and what is the load current on U6? It's 1 microamps. So let's add that, plus minus 5%. Add another load, which is potentiometer. So on that, if you'll see, if we'll go back to block diagram, we have 3 potentiometers connected parallelly. All right, so that's why the current is 3 times. So we have 3 potentiometer of 1k. So on that we'll use the same funda, same resistive load funda that we have created earlier. So it's very less amount of current which is flowing from that, but still it will contribute to our total current, so that's why I'm doing that. So it will be 0.33 kilo ohm, all right, and almost 10 milliamps. So we'll add that. So we'll consider port 1 for this one, and port 3 will be connected to ground. Let's enter load. It is resistive, so let's enter resistance of that, which will be 0.33 kilo ohm, and voltage will be plus minus 3. All right, plus minus 5%. What happened? Okay, here you have to select port 1. Okay, now we'll add another load. Right click, add load. All right, so I'm doing that step by step, so you can also practice that. I'll add the design on our description. You can download it directly. So another is U5, which is directly connected. So it's again a chip, and load current on U5 is 26.4 milliamps. 26.4 milliamps, plus minus 5%. Okay, let's add another load, and that will be through ferrite bead. So it is again a chip. 3v3 will be connected to FB4, and this will be connected through U4. Total load current on that is 1.1 microamp. So let's mention that, plus minus 5%. Okay, and let's add our last load, which is again a chip, and it is coming from FP2 and U2, and load current is same as before, 1.1 microamps, plus minus 5%. All right, file, save. So this is our network which is ready to simulate. Let's click over analyze button. Alright, so here we got all the test cases executed really well, because we have entered all the information correctly from our power budget. And let's go to our visual inspection. So we'll start from our first network. Go to visual inspection, select voltage, and left click over highlight peak values. So I just wanted to see what is the difference between maximum and minimum voltage and where it is, and so we can capture it on our report, and later we'll see if it is really critical, we have to resolve it on our design. So for VM, the maxima is fine, which is 15.5 volt that we have entered, and minima is also fine, which is 15.5 volt. So there is no voltage drop on this track, either on top layer or bottom layer. Let's go to current density, and here I wanted to see the maximum current density, which is little bit critical here, which is 48.2 amps per mm square. So we'll make sure as per IPC standard it is enough or not. So for that we'll just capture this, capture image, and this is our screenshot 1 for VM, and here we'll mention the current density that we have observed is 48.2 amps per mm square. Save changes, done. Apart from that, we'll see the minimum. So minimum, obviously it will be 0. Okay, let's go back to our another network, which is 5 volt visual, and here we'll verify voltage first. So maximum is 5 volt, minimum is 5 volt. This is fine. Let's go to current density. Here the maximum current density is 238 milliamps per mm square, which is fine, and minimum will be 0 somewhere. Okay, so here we don't need to capture any waveform because we know it is under limit. Let's go for 3v3 visual voltage. So we will see if there is any voltage drop or not. 3v3 waveform is also looking fine. So for voltage, maximum is 0 volt. Why it is showing 0 volt? Okay, maximum is showing 3.29. All right, so there is 0.01 volt drop, which is fine for me, and minimum is also same. All right, so this is again fine. Now another step is we need to observe ground plane. So we'll go to visual, select ground plane. It's quite green, which is not an issue for our case. Here we can see a dark red. Let's see what we'll find. We'll just uncheck all the VM waveforms and look for maximum voltage. So on ground, ideally the voltage should be 0 volt, but here we are seeing the voltage is 5.4 millivolt. That means something is coupling here, and we need to resolve it. So for that we'll just capture, and this is on ground, and the voltage we are seeing here is 5.4 millivolt. So obviously we have to increase the area of that ground. I guess it is on another layer, and then the problem will solve. So because of impedance or something, there is some voltage drop. Minimum will be 0, which is fine. Let's check for other grounds as well. Uncheck that. Okay, it is the same thing, I guess we are getting. So this is the only problem in our design, which is ground, and there are few problems with current density of VM on VM only. With 5 volt and 3v3 it is fine. All right, let's generate the report. If you want, you can check for second point as well, so which is kind of on the same area, right? So if you want, you can capture those waveform until the voltage is acceptable. All right, and same thing you can do for VM current density. Let's generate the report. All right, okay, report is generated. I just wanted to see if all the waveforms and all the screenshots are captured or not. So this is our design stack up, artwork. Okay, this is our PDN information. If you want, you can change that setting anytime. I just went through those, and we are using all the defaults parameter. If you want, you can use other standard parameter as well. Okay, this is again fine. Okay, here we have captured all the waveforms. For 5 volt, there is no waveform. For 3v3, all right. So there are waveform mostly for VM and ground problem. All right. So we have to resolve those on our design. So yeah, this is what I wanted to tell you on level 4. And with that, we are closing this series on PDN analysis tool. The next idea is to create a series on PSpice using Altium Designer. Let me know your suggestion, what you wanted to watch or what you wanted to learn from Altium tool. Thank you.